So, welcome to this wonderful quest on power. Now, it has been a very interesting chapter, I'm sure you would agree. We've looked at work, and then we looked at energy, and now we're going to look at power. So, what do you understand by the word power? So, a magician will say, I have powers. And a politician or a government official, like the president of your country, will say he has power. And some countries, like the United States, will say that they are superpowers. Now, in fact, if I wanted to ask if there's electricity at my school or my home, I would ask, is there power? So the word power seems to mean a whole lot of different things to different people. In fact, if you search the internet for the word power, it will tell you that power is defined as the act or the ability to do something in a particular way, or even the ability to influence or direct the behavior of others or the course of events. Now, in physics, power seems to have the simplest meaning. It simply means the rate at which you do work. Now, what this means is that if work is being done on a body or an object, the power is given by how much of that work was done under a given duration of time. So remember, we're talking about work in physics, the physics definition of work. So you remember that example we keep talking about, if you push or pull your classroom desk across the floor of your classroom, you're doing work, remember? Okay. Now, the power you use while doing this does not just depend on how much energy you spend, but also on how fast you spend the energy. Now, let's look at an example. Let's say, for example, that you push the desk across your classroom floor in 10 seconds, whereas your friend Jerry, he pushed the same desk across the classroom floor in just 5 seconds, so he was much faster than you are. Now, what this means is that both of you put in the same amount of energy. That is the energy required to push the desk across the classroom floor. But Jerry, he put in more power than you did because he pushed the desk faster than you did. So how can energy be the same and power different? Let's illustrate this using numbers. Now, if you apply a force of 100 newtons to push the desk across the floor of your classroom, which is a distance of, say, 5 meters. Let's say your classroom is 5 meters long. Then how much work would you have done? Remember that work done is given by the force applied multiplied by the distance moved in the direction of the force. This is given as work done equals force times distance. So putting in the force of 100 newtons and the distance of your classroom as 5 meters gives you work done to be equal to 100 times 5, which is 500 joules. Now, if Jerry applies the same force, 100 newtons, to push the desk across the same distance of 5 meters, then the work done by Jerry will also be equal to 100 times 5, which is 500 joules. Okay, let's look at power. We've looked at work. Now let's look at power. Now, since we earlier defined power as the rate at which work is done, we can write it mathematically as power equals work done all over time taken. The SI unit of power is the watt, which is written as capital W. Now, if you spend 10 seconds to push the desk across the floor of the classroom, then the power you put in is equal to the work done, which we've calculated is 500 joules, remember, divided by the time taken, which we said is 10 seconds. And that gives you what? 50 watts. Now, on the other hand, our friend Jerry, he spent just 5 seconds to push the same desk across the floor. Then the power he put in is equal to the work done. Remember, we calculated is also 500 joules. But Jerry did it faster, so he did it in 5 seconds. And that gives us 100 watts. Now, can you see the difference? You both used the same amount of energy, that's 500 joules. But Jerry used more power than you did. And why is this? It's because he uses energy at a faster rate. In fact, when I say that the power you used was 50 watts, all I'm really saying is that you use 50 joules of energy every second. Whereas when I say that Jerry's power is 100 watts, what I'm saying is that he uses 100 joules of energy every second. And that's it. So power, which is measured in watts, can also be defined as energy per unit second. This is why some scientists also just use joules per second as a unit of power. And we can figure this out from looking at the formula of power. Let's look at that formula again. Okay? So power is equal to the work done all over the time taken. Work done over time taken. So the unit of power will be the unit of work done, which is the joule. We all know this. And the unit of time taken, which is the second. Fantastic. So let's recap here. In this lesson, we have looked at the concept of power and how it is different from energy or work done. And in summary, we said that power is the rate at which work is done. It tells us how much energy is used in 1 second. So the SI unit of power is the watt. And we also learned that 1 watt is the same thing as 1 joule per second. Now, in the next lesson, we're going to go deeper into this and we're going to look more at how power is measured with a few more examples. So until then, keep studying and keep watching, and I'll see you in the next lesson.